So see if you can warm up on this problem. We kind of left up off on here. And we just been given this equation, given hints about the units. So as people still walk in, see if you can maybe start that, think about that. Got your units, of course, so just start looking at the problem and see how you might approach it. Question? The activity series?
Yes.
Let me see if I have it. Oh, yeah, you did. All right, let's start kind of going through this. And again, right, just a reminder, we are taking all these words that are up here and kind of, looking at these qualitative conditions and saying in general when we might expect a reaction to be spontaneous. And now, of course, right now we're quantifying it. We're getting into the weeds. And then things that I wanted you to notice. So again, like we had mentioned, let me see if I have the chart handy. So on our standard entropy chart, and maybe I should pull up this full one so we can see the comparison. So the problem is our units are different, so we just have to be aware of that. So again, enthalpies tend to be given in kilojoules since they are larger, versus your entropy value is given in joules. So okay, things to watch out for. And then you could have started to plug all these values in. So not too hard at least, right? So we have all these elements from our equation. And then luckily they gave us the delta H and they gave us the change in entropy, right? But we could have calculated that from just a standard data table, right? So summing up our carbon, looking up the enthalpy of that, plus 2 equivalents of chlorine. And so we'll practice that later, but I just want you to have that in the back of your mind that, okay, we could have solved this, but they did give it to us, and that was nice. And so now let's just proceed. So delta G equals our delta H, kilojoules. I'm just keeping track of my unit. Minus, and then of course, watch the temperature, right? We should be in Kelvin, like we expect. Again, we need a thermodynamically relevant unit. So 298. And then again, don't forget to convert. So then let's see what we get. And so I got that value. So is that what other people got as well? Let me know. Yes, no. All right, some yeses. Did we get, okay, thumbs up, excellent. So we all got this delta G, 53.32 kilojoules. And then do we remember what we said about delta G? What was the value that it had to be spontaneous, positive or negative? Oh, try again, next guess. Yeah, negative to be spontaneous. And so where can we highlight that?
Is that like a conditional thing, or does it have to be negative to be spontaneous?
Yeah, it has to be. So that's part of our notes here. So delta G has to be negative to be spontaneous. So that's part of the mathematical conditions. So yeah, star that, whatever. That's kind of confusing because it's negative. So it's like a little different in our brain. So delta G has to be negative. So then now we can say we have a positive value, so not spontaneous. At least, again, at this temperature condition. So perhaps, right, if we can just kind of glance at this mathematically now. Obviously, we could solve it algebraically. And that's actually what the next question asks, right? So if it's not spontaneous at 25, determine what temperature, if any, the reaction becomes spontaneous. So go ahead and try that then. And then from the chat, the suggestion is to set delta G equal to 0, right, to get right at that point. And I see nods, so okay, it looks like that's what everybody did. Okay, so now we can just set up our algebra. So I'm just kind of rewriting our formula for a second. And then set those two equal to each other. And plugging in values now at this point, just algebra. Again, keep your units in mind, 0.1422 for the kilojoules of our change in entropy. Trying to solve for T. And so what do we get?
I got like 673 Kelvin and 4 degrees Celsius.
So 673. So I believe got the same thing. And then, excellent. See more thumbs up, nods. Sounds good. And then, of course, that was in Kelvin for our temperature of 673. Again, I just watch on the exam what units. I generally don't care unless it's specified. All right, questions on those?
Could you go back to the chart that you had for the initial color? I was confused because it shows that at low and high temperatures, it can be spontaneous or non-spontaneous. And
Yeah, so we can think about what it's saying, right? So we can kind of look at this chart here. And so we look at our conditions, right? Let's just kind of rethink what kind of reaction this is. Well, we have an endothermic process, right? Because we have a positive change in entropy. So, okay, we're saying that we have something where it requires energy. So kind of looking at these two conditions, right, from the chart. And then it's saying, well, at a high temperature, perhaps it could be spontaneous, right? It kind of depends. And so in this case, if we look at kind of where it's always non-spontaneous scenario, the change in entropy was negative, right, for this line here. So this is saying that it's going to be non-spontaneous under all conditions, right? If you're going to have to add heat to it, but then your entropy is decreasing, right? That's kind of somewhat contradictory as well, versus what our actual scenario was. So it was, again, endothermic reaction, but then increasing entropy. So then, yes, it is spontaneous, right, under high temperatures, which we then did prove. So, okay, then we're saying, yes, once we get it to 673 Kelvin, then it is spontaneous. And so, right, you can think about where this might be relevant. Again, kind of more on the engineering side of things. If you're trying to plan out your big reactor, you got to calculate, okay, well, what temperature do I even have to get this reactor at, right, to get this reaction going? So that goes into, efficiency of your reactions and all those good things, right? Starting to get into more of the chemical engineering side of it. How are we going to make this an efficient process? Again, if you're requiring energy too, you really want to be able to control that and just make sure that it's an efficient process. All right, so now let's go back and relate our equilibrium constant to our G. And again, we'll kind of pay attention to the signs. All right, so let's see what it is saying. So if our K is less than 1, and again, we kind of have to think about what K was. So products over reactants, right? It's just a measure of how forward it's going.
is K degrees Kelvin or is that like?
So remember, K is back to equilibrium K.
Okay.
So the same K that we've been talking about, right? Like any equilibrium expression, which hopefully we'll get to examples. That's my goal, so we'll see more of this. And okay, so if K is less than 1, right? It's saying that it's going to be favoring the reactants. And then so delta G is positive, so then that's saying that that's non-spontaneous. And then the reaction then would be spontaneous in the reverse direction. So then, right, nothing would happen though if there were no products, right? Because then it would not be able to go backwards. And then, so then if K is greater than 1, again, it's favoring the products. G is negative, so then that's saying it is spontaneous in the forward direction. So again, right, kind of both statements have to agree that both your K is saying it's favoring the products, and then G, again, has to stay that it's spontaneous. And then if we're at our equilibrium conditions, K, of course, is going to be equal to 1, and delta G is 0, so then we know we're at standard equilibrium. And then these are kind of more confusing statements, right? So we have to, again, think about what they're trying to say. And so we have Q. So remember, Q is just our snapshot. So then, okay, if Q is greater than Kc, then we're saying that the reaction goes backwards. So it's spontaneous, right, in the backwards direction. And we remember that, right, from equilibrium, because we're saying we shot past the equilibrium point if Q is greater than 1. Again, just trying to break it down simply, right, products over reactants. So then we expect it to be favorable, right, in the backwards direction to get back to K. And then, okay, if Q is less than K, right, then we know it has to go in the forward direction. So we set that, again, just equilibrium. And then, of course, equilibrium conditions. All right, so now we have our equation to relate that. And so the other important thing to just note is it doesn't matter whether we're talking about C, QC, like concentration. So again, recall that this is for molarity concentration versus the QP or KP, where we talked about partial pressure. So you can apply them in the same way, right? We're not trying to go back and forth here between Kc and Kp right now. We're just focusing on either one. And so the equations are the same.
I did have a question about the initial formula for the complication. Notice it doesn't have any subscripts, so does that just indicate that it applies to every single K, regardless if it's K sub F or K sub B?
Yeah, exactly.
Okay.
Yes.
K sub F is the rate of the forward reaction, right?
K sub F is K formation.
Formation. Okay.
Yeah. So just like when we were doing the ionic compounds.
I googled it and it was giving me like K sub frozen, K sub.
Yeah. Well, there's probably lots of variables too. All right, so then we have, so I would star these relationships. Again, right, you can kind of ignore the C or the P, just as long as you're not trying to go back and forth between the two, which I wouldn't expect that in this case. And so then, again, we can get our delta G, and negative is, again, spontaneous. And then our R in this case, you could maybe guess it, but it's 8.314, our joules per Kelvin. So our energy. So we have R, and then again, T is Kelvin. I think that should go without saying, but we'll be explicit.
If you were to swap the K and the Q there on the fraction, would you then have a negative RT with the equation?
Yeah, so you could do that. And so then what we expect, so again, right, if our Q is greater than our Kc, so it's greater than 1, then this value should be positive, so right, saying that it's not spontaneous in the forward direction. And then if it's less than, then we expect our delta G to be negative, again saying that it is spontaneous in the forward direction. And then of course at equilibrium, we expect the delta G to be 0. And so again, just keep that in mind that if your delta G is positive, right, it just means that it's not spontaneous in the forward direction, but it could be spontaneous in the reverse, which we've, again, seen, right, just from our equilibrium. And then, sorry, my arrows got dropped there. So now see if we can calculate this. So it's asking you to do your delta G. And so again, right, just like we can sum up our enthalpies or entropies, we can do the same for delta G's if we are given, again, our values. So write our, oops, not the sum, our overall change in Gibbs free energy is again equal to the sum of our products, and N again indicating that we should multiply it by the correct number of moles minus the sum of our reactants. So try that. It just wants you to practice that, and then you can plug it in to our formula. Negative G equals RT ln So just try that for a second.
What's the value for R?
All right, so start kind of walking me through. So what do we get for our change in Gibbs free energy? So delta G, so we did 2 times our products minus reactants. So what did you end up getting for your difference?
I just jumped straight into the formula there.
We had to get the delta G to get the K, right? Because we have to figure out our Gibbs free energy because we weren't given equilibrium constant.
So
So 2.8, and then what are the units though? Kilojoules. And then, right, per mole, but we already multiplied it by the molar amounts. Now we're just at kilojoules. And so the only kind of tricky part is this constant was in joules though. So I would convert this to joules so we're all in the same unit. So 2,800 joules then is equal to, now we can just plug into this equation, negative R, so 8.314. What T are we at? So 298 Kelvin, so that's fine, times ln of K. And so now we can just algebra, and so you can let me know what you get for K while I punch this in. Then I have something, so negative 1.13 is equal to ln K, and then right, just take E to the power to get rid of that 0.99. I'm not sure, let me, because I get this number.
Divide by 8,000.
What do we get for K? Because I get this value of 0.323 for K, so I see some other confirmations. We get this number. Okay, yes, sweet. I'll make sure we're on the same page. Questions on this one? Yeah. This one, the 51.3, that's just, they gave it to us, right? Yeah. And I think though that could have just come from, again, like a standard chart. So if we look up NO2 on this chart, let's see if they have it. Where's nitrogen? They have to have nitrogens. There we go. So yeah, NO2, if you were to just look this up on a standard chart as well, so the middle one is the Gibbs free energy, so that's where they got the 51.3 value from. So if it wasn't provided, you know, again, on an exam, I'll probably give you all these relevant values, but, you know, once you're off in the real world, know that you can look these up. That's where they came from, right? Same thing for this N2O4. We can look it up on a standard table. Let's see, so N2O4, so again, slight difference in numbers, as you can see. So this one has 97.89, so pretty close. But yeah, that's where they came from. So they're, again, standard thermodynamic values. All right, other questions about that one? All right, so then the next piece of this puzzle is then putting it into our temperature dependent kind of 2-point form equations. And so we have, again, we just learned these ones in our chapter. So we have, of course, right, we just proved this one, and we have delta G is our change in enthalpy minus our temperature times our entropy, and then we could relate it to K. And so then just rearranging for this, right, so substituting in for G, and then dividing by R and T here, you can see. So, right, all we did, sub here into there, and then basically set it equal to ln K. So then they get this relationship. And now we can start to see how we might plot it out. So we have this general form. So y equals mx plus b, so whatever variable here. And so then that means if we graph it, so we graph the natural log of k, and then notice, right, it's going to be 1 over t to correspond to x. So that's why you do inverse t. So this should give you a straight line, and then our slope is going to be our change in enthalpy over r. So again, right, you could just multiply your slope by r, still 8.314. Then you could get, right, your enthalpy. And then your y-intercept then would again be equal to your change in entropy over r. Again, same thing, multiply. And then the other form, so this is nice, but then your book has two other forms of the equation which are going to be useful. So let me write them. And so we have our Van Hoff equation from our book. Again, another 2-point. So this is going to be for when we have kind of 2-point temperature, right? So this is nice if we were in lab, right? We're plotting something, maybe trying to solve for both of these or one of these values, right? So you could make a plot of the K values. Or, right, we typically kind of see these 2-point equations. So then our 2-point equation would be our natural log of K2 over K1, right? Again, temperature dependent is equal to our change in entropy of the reaction over R times T2 minus T1 over T1 times T2. And right, T again is always in Kelvin. Right, these are just equilibrium. And then we could also have the same for pressure. So Clausius-Clapeyron equation, which I probably misspelled. So this is just, again, for gas. So it's going to be very similar, so as you might expect. So now it's just P2 over P1 is equal to delta H vaporization over R times T2 minus T1 over T1 times T2. All right, so those are good equations. Let's do some practice. All right, let's try. So I'm going to flip over to some book problems. And so let's just start with the first one here. So now we're kind of going back to equilibrium again, right? Just this goes back to, we can apply it to any equilibrium scenario. So we can apply it to even, right, our weak acid. So we're looking at nitrous acid. So you can remember, right, that's one of our weak acids. Looking at it in water, So of course, our weak acid, right, has some sort of dissociation to make hydronium. And then there's our conjugate base, nitrate. And so we're given our equilibrium constant at 25 degrees Celsius. So see, we can figure out our delta G. And then you can just begin with the first conditions. So will it be spontaneous at 1 molar? And then we can look at the second set of conditions. All right, so how do we approach this one? What do we need to do first to calculate our delta G of our reaction?
You start by converting Celsius to Kelvin and multiplying that by R, so it's -8.204.
So then what formula did you plug it into?
Change of G equals negative RT times delta K.
Okay, so then just start plugging it in. So negative 8.314 times 298. And then they gave us our Ka, right? So natural log of is 5.6 times 10 to the negative 4. And so then when we plug that in, make sure I don't drop my sign here. So do we get a positive or negative number?
I got a positive.
So that's what I get as well. Do we get this number? All right, so we get that delta G, and we can convert this because, right, this was in joules, so I'm going to put 18.5 kilojoules. So again, positive, so not spontaneous. And so then let's check it at these various conditions, right? So then all we want to do is just like before, so let's plug it into our K expression and get our Q, right, and compare. So for the first set, they told us that everything looks like everything has 1 molar concentration. So then we can plug it in. Again, just to our equilibrium expression. Now I'm just going to write out, so Ka conjugate base times hydronium or H plus over HA acid. So then our Q, right, is 1. That was kind of, oh, I don't know why I wrote I. So. Yeah, I got excited there. And so then we can plug it in to our other equation. So delta G equals RT, ln of Q over K. So then what do we get for this expression? So 8.314 times 298 times my natural log of 1 over now my K. So, right, still positive, which makes sense. So this is kind of our 1 molar standard conditions, right? So, okay, not spontaneous. And then we can repeat that. So then it says for the second scenario, now our our conjugate base and our acid are 1 times 10 to the negative 5th. And our nitrous acid is 1 molar. So now we can repeat that process, right? Plug it into our Ka so we can get our Q. So Q is 1 times 10 to the negative 5th squared over 1 essentially. And so now plugging into, so delta G equals RT times natural log. And so negative 5, right, squared is just negative 5 plus 5. So 1 times 10 to the negative 10 over dk. And so did we get this number to be spontaneous? And we can kind of predict too, right, from our K value, or from our Q and our K, right? So our Q is less than K, so I do expect it to go in the forward direction. But again, let's just mathematically verify that. Bless you. Natural log of this. Oops. And so now we get a negative delta G. And again, right, that does kind of make sense just based off of our equilibrium and what we expect to happen. So negative 3, and I'm going to change it to kilojoules, so 38.5 roughly kilojoules.
Is G ever expressed as anything but delta G? Is there any absolute value for G?
I'm not sure. Yeah. I think it's usually measured as a delta because it has to be like energy available for work, but I don't want to misspeak. So let's see what levels would be good. Sorry, I'm trying to figure out which one I want to do. Let's actually try, I'm going to put another one up there. Bless you. Springs in the air. So let's try this acetone one, just because we want to practice these two equations I kind of threw at you. And so now we can see where they're going to be relevant. And so acetone is obviously a widely used solvent, a really great one, and used in nail polish remover sometimes, unless they use ethyl acetate. And it has a normal boiling point, 56.05 degrees Celsius, and a molar enthalpy of vaporization. So there's the value, right, that was in our equation. So again, right, this is where it's going to come in from, so it's going to be given. So our enthalpy of vaporization is 29.1 kilojoules per mole. So calculate the equilibrium vapor pressure of acetone at 20 degrees Celsius. So go back, look at that equation. Yeah, the Clausius-Clapeyron equation. So this one. Right, so we had all those values there. So kind of think about what is what. And I can flip back to the problem too. And this is just 47 from your book. So again, your book has excellent problems. That's why I like your book so much. Yeah, so that's what it's delta H vape that's in your formula. That's what it's referring to. And you may have to recall what this means. Normal boiling point. Always. So let's just kind of start setting it up together. And so it doesn't really matter who you call P2 and T2, just as long as you're consistent. And just for my own sanity's sake, I might just put T2 as the higher one that we're talking about. So 56.05 degrees Celsius. So I'm going to convert that to Kelvin. It's about 329 Kelvin or so. And then, so if this is T2, then my P2, and then you had to remember what the definition of normal boiling point was. So what pressure are we at? What was normal boiling? What's our normal ATM or pressure?
Is it one?
Yeah, so 1 ATM, right? So, or since it wants it in torr, I went ahead and just went with torr. It doesn't matter as long as your pressure units are the same. So 1, again, would be appropriate, and then just convert to torr since it was asking you in torr. But yeah, just as long as it's normal boiling point. So that was back just a definition. And, okay, so we got our entropy. I'm going to change that to joules. Again, just because our R is in joules. So I don't want to make a unit, oopsie. And so now I think we're ready to plug it in and solve. Oops. So we're trying to get our new vapor pressure at this temperature. And so now it's just plugging and solving. And then this is just 293 Kelvin. And so you can let me know your answer while I plug away.
Yeah, like 1.3.
1.3? You mean, I get that for like the natural log, like the ratio is equal to 1.3, at least in my notes.
0.001.
Times, oh, I should have done this first in hindsight. Yeah, so right now I'm here with my natural log of my P2 over P1 is equal to 1.307.
Did you get someone at 60?
Oh, I used, yeah, torr. You could have used 1.
No, 64 is my answer.
Yes. Oh, so what was your final answer then in ATM?
I got 0.998 for X. If you want.
That sounds funny. I think you might be off. So then E. It shouldn't matter which pressure unit. Here's my E. Oops, wrong thing. So then I get something of the ratio 760 over P1 is equal to 3.69. And so I get like 205 or 206 torr roughly. You did it in ATM, you should get 0.27.
What happens is I use the referential answer, and then I redid the equation, and changed the answer, so I got way smaller.
All right, so did you get 206 torr now? And do we all get that? Okay.
Yeah.
Sweet. Okay, we're kind of running out of time. I'm trying to figure out what I wanted to do next. So let's see, because we have this one, so 71 is kind of tricky, but it's also kind of good, because it's like solubility practice, which we could do. This is just signs. That's more 2-point stuff. Let's see. Let's just try 71 because it's hard, and then we'll end there. So we'll go a little long, but this is kind of good, and it'll help us prepare for your quiz. All right, so let's kind of look at what we're doing. And so, right, we have our solubility of lead iodide is measured as a function of temperature. And we have this data here. So temperature, solubility. And so it wants us to calculate the value of delta H for the reaction for the dissolution of this. And then we'll compare. So how might we do that? What equations do we have? What do we have to calculate to? Right? We're just given this solubility. And so before we get too into the weeds, what do you notice about your solubility too that you need to maybe fix before you start calculating K values?
It's in grams per liter.
So it's in grams. And so what should we do then?
Try to convert it to the moles per liter, the molarity.
Yeah, so do you remember how to do that? So we have, right, if it's given in grams per liter, what do we need to do then?
We need the molecular weight, lead.
Yep. And so I'm going to look it up because I don't feel like adding today. And so I have a molecular weight of lead iodide as 461.01 grams per mole. So right, we can see how we can divide. So 461 grams mole. So we get back to our molar solubility. And so, right, watch that on the quiz. It may ask for gram solubility. It may ask for molar, right? You might have to convert back and forth. And then, so we can kind of walk through this together since we're running out of time. But then we want to pick 2 points, right? It doesn't really matter what 2 points we pick. I'd probably pick just the most extreme to try to get like good data. And so first we need to convert that to, again, our molar solubility, and then we can plug it in. So I'm just going to sketch this out again so we can see where we're going with this. So we'll have, right, molar solubility once we calculate that really quick. And then, right, 1 equivalent, 2 equivalent, plugging in for KSP, right, S times 2S squared. And so we can get this 4S to the third, which some of you may remember the formula, so you could have just skipped right there. I just, again, I personally like to rederive it. It really doesn't matter. All right, so let's start doing that. So now I'm just going to put numbers. So I'm starting with my gram solubility, dividing it by 461 to get my molar solubility. And again, so I'm just kind of rewriting everything here. So 1.25, or I guess I'll round it to 6, times 10 to the negative fourth. And so then we have to get our K, right? So now I can just plug it into this formula conveniently. So to the power of 3 times 4. All right, so there's 1 K SP. And let's see, try not to round too much, but. And so then just repeat that again, right? You can pick any 2 points from this data table. I'm just going to pick this one since, again, it's the most extreme, so I like to get 2 extreme data points if possible. And then again, right, convert to molar solubility. Oops. So 0.366 divided by our molecular weight. Just repeating that. And so then new value, so I'll just kind of rewrite that. So molar solubility at 80 degrees Celsius is equal to this 7.94 times 10 to the negative fourth. And then again, now I'll just plug it into this. So to the third power times 4. So now we have our K value, which is what we really cared about. 2.002 times 10 to the negative 9, roughly. All right, so now we're here, and that was a lot of work to get our K values, but now we're finally ready to plug into our 2-point form again. And again, I think that was just a valuable problem to see. And so now we're here. And so now we'll just say, okay, well, we're ready for 2-point. And so, right, that's our equation that we kind of saw at the end. So going back to this one, right, our Van Hoff equation, our 2-point temperature. So now we have our appropriate Ks. So we're ready. And you can see, again, why this is a starred problem. So lots of steps to it, but again, right, you're going to have to be doing parts of these steps. All right, so time to plug it in. So I'll just write the formula first. So we're trying to solve for our change in enthalpy of our reaction. over arc, so just watch those units. And then T2 minus T1. So I'll, again, set T2 to the higher one. Doesn't really matter, just as long as you keep T2 with K2. So now we're just plugging at this point, now that we solved for all our variables. And then, of course, converting temperature to Kelvin. So 353 minus 283. Again, just with the 2 points I picked. All right, so then I get my delta H of the reaction to be so 65,643, but then that's in joules, right? Because that's based off of my constant here. And so that's about 65 kilojoules, or 65.6 kilojoules, which matched pretty well with the accepted value there. So that was pretty nice. So did we all kind of get that? So really you just had to get to this point, and then from there I think you're getting good at plugging in these 2-point equations. All right, other questions, comments? So I'll probably end there since we're already a little over. But we may go back and kind of practice these, or, you know, I would look at these if you have some time perhaps. And yeah, you should be able to calculate them. So your book is a great source of extra practice. All right, I'll go ahead and end lecture officially, and then you can take your break, of course. The quiz is a little shorter, 8 questions, just because there's some calculations, obviously. So again, just watch the units. So the first one is asking for your solubility in grams per liter, so not molar solubility like we're used to. So just pay attention, don't just go on autopilot. And then for the other questions, right, you're thinking of common ion effects. Look at the acid-base equilibrium. Oops, sorry. And then, of course, if you need to take a break, take a break. Obviously, very math-heavy lecture today, so definitely take a little break if you need it.